Hi, class. I hope you all are doing well. I know this time of the quarter can be a little bit overwhelming. Hold on, let me close my window so we can have a better production environment for this pre-class exercise. This week, we're mainly going to continue working on regression. This is the workhorse of what you're going to be doing in Stata, so I really want to make sure you feel comfortable with it. So there are a couple of different things that I wanted to show you we can do with linear regression. The first thing that I want you to get comfortable with is that often you will be in a situation where you don't necessarily have data, but you might want to start to scope or understand a problem. And one of the ways you can do that is with simulation. So that means you generate data and you write code, and then you can try and model things based on explicitly or implicitly stated assumptions about your data. So let's create sort of a fictitious case of where we think these types of tools might be relevant. So in this case, imagine we are working with some hospital data. And one of the things that they're interested in is the effect of a drug on a patient's O2 saturation. Higher O2 saturation is better, but there's some concern that a subset of patients might be allergic to this drug. In addition to that, we also know that certain individuals, particularly those who are vaccinated, might just have better outcomes in general. So what we can do is we can sort of generate the true underlying data and see how well we can capture some of these expressions with linear regression as our toolkit. So what I'm going to do here is first I'm going to randomly generate our data. And what we can do, if you're not familiar with simulation, is that we generate our dosage as being uniform from 0 to 200, meaning that on average, a patient should get about 100 milligrams. But there will be a good deal of variation that if you plot the histogram of dosage, we should see something that looks pretty uniform. And yeah, looks pretty uniform to me. There are some odd spikes, but we know the true data generating process, so we can feel pretty confident that it is uniform. And when we look at the mean, I said it should be pretty close to 100. Let's see what it actually is. 97, so pretty close. And if you wanted to get a better sense of that, we could do the associated confidence interval. So that is the CI means command. And we see that it contains our true data generating process is mean that our confidence interval is between 92 and 102. And we know that the true mean of this data of a uniform random variable is just the midpoint. And we can do the same exercise with whether or not a patient is allergic. So we generated it with a 20% chance of an individual being allergic. Let's check and confirm that that's the reality. And we're going to use the CI means command to see if that's accurate. Again, it contains our true point estimate. Again, these are 95% confidence intervals, so sometimes through sheer random chance, we will not include our true point estimate, but generally we've got a pretty good chance of doing that. And just really quickly, we're going to do the same thing with vaccination. We generated that individuals were about 80%. And in fact, I probably should be doing this as a proportions test. You can read the help file and learn a little bit more about what these do. They're pretty similar. Basically, when I use CI means, it uses a normal approximation to generate this confidence interval. When I use the proportions argument, it uses a slightly more precise technique to estimate this confidence interval. So it doesn't make a huge difference, just to give you an idea. But if you, say, are taking a statistics course, they might ask you to calculate things exactly versus, say, using the normal approximation. So that's something to keep in mind. Yeah, so we've generated our underlying data, and now we actually need to generate our outcome variable. So what relationship are we going to specify for oxygen saturation as a function of dosage, an individual who's allergic, and whether or not they're vaccinated? So I chose to assume that the drug we selected was effective, but not super effective. That for each additional milligram a patient received, that they would have about a half 0.5%, 0.005% increase in their O2 saturation for every milligram they received. This is just to make the numbers feel pretty interpretable. Then we also assume that individuals who were allergic to this drug would have a negative reaction, that their O2 saturation would drop by 2 points, and that individuals who are vaccinated, that they would tend to have better outcomes, and that they would just generally have higher O2 saturation. So now let's model this with linear regression and let's see what happens. So we're going to generate our true data. And when we regress the three variables that we know actually can exactly predict the relationship between O2 saturation and our three outcome variables, we do exactly that. That we estimate a dosage such that for every milligram, you see a 1/200 increase in O2 saturation. That if you're allergic, you're going to get a slightly worse outcome, and if you're vaccinated, you're going to have a slightly better outcome. And the other thing that I want to highlight, when you exactly predict these types of relationships, that you actually aren't able to estimate standard errors because you don't have any variance. So you're you're in this weird space where your standard errors are actually kind of zero. So if this happens, it doesn't mean you did anything wrong. It just means you were able to exactly predict the relationship. So I didn't want you to be surprised by that. The other thing that's sort of neat, and we talked about this a little bit in the prior week's exercises, we can generate predictions. So after you run the regress command, you can generate the predicted values using the predict command. And you can also generate these things called residuals. And what you should know about residuals is that basically is a measure of how off was your predictive model for each given observation. And there are a couple of neat little properties about residuals you should know. That on average, if you're using linear regression as your model, that your residuals need to average to 0. And ideally, we'll talk a little bit more about what a good distribution of residuals looks like, but generally you want to see them be unstructured, so a cloud of points. If you can sort of see a structure between your residuals and an outcome variable, that means you probably haven't specified your model correctly. But this, we're explaining all of the variance, so we actually aren't too worried about that. But let's show you a plot of the relationship between O2 saturation and predicted values. As you would imagine, it's going to be a perfectly straight line because we've got an R squared of 1, and our correlation coefficient is exactly 1 as well. Now let's look at something else. Let's assume that we had a slightly simpler model, that we didn't actually know about whether or not patients would be allergic or be vaccinated. And what we see is that we actually still get a statistically significant coefficient. It's pretty close to our generating assumption. But in this case, the interpretation of our constant changes, that on average, a patient who gets 0 dosage is still going to have an increase of around 1.2 in their O2 saturation. But for each additional dosage on top of that, they would receive an extra 0.05% increase in their O2 sat. Now, typically, we aren't going to be able to understand the true data generating process. And in fact, even when we understand the true data generating process, there will often be components that are noisy or things that we can't necessarily measure with the precision that we like. So often there will be what I would refer to as a noise component. And so that's what we're going to do, is we're going to estimate this model where the exact relationship is the same, but we just have this nuisance parameter that's a normally distributed variable, meaning it has mean 1 and standard deviation. And then we're going to run the exact same regression. And let's see how much variance we explain. And we see that just adding a little bit of noise can make a big difference in this model. We still retain our true point estimates on each of our covariates. I think that is one of those sort of nice takeaways when our errors are like just normally distributed. We tend to see that things work out fairly okay. But if you're trying to exactly predict this type of model, what you can see is that the R squared is really is substantially lower than these cases, even when we know the exact data generating assumptions. The other thing that I want to highlight is that adding more variables into a model doesn't necessarily make sense. So let's just create some more random variables. Let's say R uniform 0 to 1, X4, R uniform 0 to 1. And let's just plug those in. We know how the data was generated. We know that it really should just be a function of these 3 variables plus that normal error term that we aren't able to actually observe because we don't. But we also know X3 and X4 should have no impact on improving your R squared because they're completely unrelated. But let's take a look at that just for our own edification. Oh, I forgot to include a dosage variable. And what I want you to notice, and let's just exclude X3 and X4. We see that actually our R squared increased slightly. Was 5.88, and when we had X3 and X4, when we remove those, it decreased slightly. So even when we're adding these irrelevant variables, your R squared is always going to go up. So one of the things that you should also look at as a metric for fit is this adjusted R squared. And basically what this does is adjust for the fact that as you write more complex models, and adjust for the amount of statistical degrees of freedom you have. You can see that in terms of this F test, how this 5 corresponds to the number of covariates in our model. This 3 corresponds to that, and this corresponds to how many observations or degrees of freedom we haven't used, which is just an arithmetic relationship between the number of observations and number of covariates and the remaining amount of observations. The other thing we can do is often we will be interested to understand joint relationships of variables and regressions. So for instance, I might be wondering, do I really care about whether or not a patient is allergic or vaccinated to this particular drug? So I could individually test these outcomes, and in this case, I would say they're both statistically significant, but sometimes, for instance, if we are testing things that might be related, so for instance, if these were demographic dummies, we might not want to do an individual test for every variable, but we want to jointly test all of the related characteristics. So does race predict anything in this relationship? Is it statistically significant? And all we need to do is use the test command, and that will assume test against a null that allergic and vaccinated are equal to 0. And here we see we've got a large F statistic, and the associated p-value is less than 0.05. So we feel confident in saying that that at least one of these values is not 0. The other thing we can do is try and understand how varying the dosage will affect treatment effects. So what we're calculating is something known as a marginal effect. And what this is doing is at different values of our treatment variable, seeing how, or at varying levels of dosage, what is the marginal effect of an additional milligram of dosage. And because we know the underlying data generating process is linear, that's not going to change a whole lot. And normally we could do something called bootstrapping and just sort of simulate this data a whole bunch of times and see how things vary. But I'm not going to go too into the mechanics of programming that. I just want to show you a quick for loop. And what you can see is that when we just sort of quickly scan these coefficients, generally they seem to contain our true point estimates of our data generating process, but sometimes they're a little bit higher, sometimes they're a little bit lower. I'm taking a look to see if we have any instances where things are not statistically significant or don't contain our true point estimate. And I'm not seeing any, but that doesn't mean it might not. I might have scrolled past it. But either way, I think this is a nice little example about how simulating data can be useful to understand relationships and how well you can capture things. And also I want you to see that the art, even when for the most part our model does pretty well, we see pretty big variations in the amount of variance we're able to explain. We sometimes can explain 50% of the variance, other times we can explain more than 60% of it. So yeah, I think there's a lot of inherent randomness into how well your models fit, and thinking about how you want to deal with that is sort of the key takeaway. And there are a couple of things you can do once you sort of know and understand these problems. So again, we're going to predict our predicted values and our residuals, and we're going to plot them. And generally, the things that you want to look for is you don't want any structure between your residuals and your fitted values. And here we see that despite the fact that there's spacing between all of these three clusters of points, it's very hard to estimate a relationship such that if I know your fitted value, I can tell you something about where your residuals are likely to be. And that's a good property suggesting that our model is fitting fairly well. And we're going to see an example of when our model doesn't do that. So let's keep our same drug example, except we're going to look at a slightly different outcome. We are going to look at the effect of the same drug on blood pressure. And here we're going to see that there are going to be a couple of different changes to how patients respond to the drug. So for instance, as your dosage increases, your blood pressure increases. In addition to that, it's going to have a nonlinear effect. That's this component, this 5 times dosage minus 100 divided by 50 squared, meaning that for the patients who got 200, they might actually see an increase of up to 4 points in dosage, whereas the patients who got none, they also would see roughly on the order of about a 4-point increase in their blood pressure. So there'd be the sweet spot where if you had an individual who didn't receive any dosage, or who received about 100 milligrams, they wouldn't have any change in blood pressure. In addition to that, we're assuming that being allergic and being vaccinated also have an effect on your blood pressure. And that in fact, if you're both allergic and vaccinated, then there will be sort of an interaction effect, meaning that your blood pressure will really go up. And we also include this noise component. So what I'm going to do is just do a quick linear plot of blood pressure and this outcome variable dosage. And here we can see the exact relationship between dosage and blood pressure. And in this case, we're fitting it with a straight line, and we can see it's doing a really bad job. In fact, as a human, we could probably draw a pretty good parabola through this data and give us a much better estimate of how dosage and treatment effect will co-vary. So sometimes really getting this coefficient specification right can matter a whole lot. And we can even alter this prediction and just sort of tell Stata to fit a polynomial expression of this treatment, this dosage and blood pressure change, and we can see that we already do a much, much better job. Now, how can we translate this in a linear regression model? So we can regress blood pressure on dosage, and there are a couple of different ways you might see people try and interact and understand this. So you could generate a variable called, say, dosage squared, which is just going to be dosage times dosage. And we could regress that. But I'm going to suggest we don't do that for a nice little reason here. So when we incorporate that, we do a pretty good job of capturing the the underlying coefficients. Both are statistically significant, but the thing that's sort of nice is Stata can instantly compute the marginal effect of different drugs, of different treatment effects. So as I mentioned before, effectively, when you've got these sort of polynomial relationships, that the associated treatment effect of an additional milligram will be changing. But when we do, say, marginal effects, dosage, dosage equals 100. It's negative 0.422. And let's try it at one of the extremes. And again, we see that our treatment, the marginal treatment effect isn't occurring. And that's because we generated this dosage squared variable. Now let me show you a way to estimate this marginal effect. Using an interaction term. And we know that dosage is a continuous measure. So we're going to use the C dot notation. And we want both a linear and a quadratic term. So we're going to use this double hash mark. And we can see that these are the exact same coefficients we generated when we used dosage and dosage squared. But what I want you to also see is, let's see what the marginal effect of giving a patient a milligram of the drug at when they've received none. Let's do that real quick. Let's try out a different value. Okay, perfect. So what we see here is that at 0, giving the patient a milligram of the drug actually will decrease their blood pressure quite a bit relative to giving them none. But at about 100, not so much. So what's nice about this is you are developing a toolkit to sort of interpret regression. You can predict on data, you can pull coefficients and assemble these things together, and you can also use these sort of partial derivative techniques to understand what is the marginal change and impact for patients with particular characteristics. So all of this is really nice. And the other thing that I want to show you is that you can do basically the same thing for factor variables as well as just binary variables. So let's regress our full specification, dosage. We're regressing blood pressure on dosage. And what else did I have? I had vaccination. I had whether or not the patient was allergic. And I also have the interaction of being vaccinated and being allergic. And I wanted to show you that you can also do a single interaction term, and that's what this hashtag, this single hashtag is. Because I already specify vaccinated and allergic here, I don't need to specify, I only need to specify the interaction. Yeah. Sometimes the interpretation can get a little bit wonky. So what I'm going to do instead is I'm just going to delete this vaccinated and allergic term to make it a little bit more interpretable for myself. And I'm going to do this double interaction. So now this is the associated effect of being vaccinated. This is the associated effect of being allergic. And this is the combined effect. And again, even though, well, now we've actually captured most of the relationship. So we've got a pretty high R squared, but it contains most of the true parameter estimates in each thing's associated confidence interval. But now let's run through and do that same marginal effect of, say, being vaccinated in this case. If a patient is allergic, This is the other thing that I wanted to highlight, is that when you use these marginal effects, sometimes, particularly when you're working with factor variables, they will not necessarily be cooperative. So you might want to use a different expression. So you instead want to use this command margins. And you want to specify an associated variable. So what this does is let me know what is the marginal effect of being of having a change in vaccination status at different points at the mean for each group. Another way I can do this is actually compute margins at different points in a covariate outcome. And so this is telling me the marginal effect of being allergic at different conditional on an individual being vaccinated. And we can see that we have nearly a 13-point increase between these two outcomes. Yeah, so you don't necessarily need to take away all of these techniques, but I just want you to know that this capability exists within Stata. And finally, the last bit before I leave you to work on this exercise is to show you an example of a misspecified model. So we're going to regress blood pressure on dosage. And here, what we see is we've got our residuals and our fitted values. And what I can tell you is that there's structure here. That you can see that there's clearly a parabola. And so you know that if you can predict the value of the residual as a function of something like your fitted values, that means that you're probably not capturing the true relationship. So you want to include that. I'm going to leave this as an open-ended exercise. I just want you to play around. So the things that I'm going to encourage you to do for both the blood pressure exercise and for O2 saturation, try different parameters for the mean and standard deviation of the nuisance parameter. That's the R normal variable. What happens when you increase the mean? Where do you see changes in the associated coefficients? What happens when you increase the standard deviation? Does your R squared change? Do your coefficients change in response? And the last thing is just also try representing your dosage variable in different formats. So if you try, say, replacing it and converting it from milligrams to grams, how does your coefficients change? With that, I'm signing off, and I will see you Tuesday.